It is my great honor to introduce Dr. Ahmed Mousa. He is a very well-known figure here, and Dr. Ahmed Mousa earned his PhD from the University of British Columbia in healthcare and epidemiology, and he possesses extensive experience in ophthalmic research, teaching, training, and community work. He served as an assistant professor in King Saud University for more than eight years. And he has 112 publications to his credit. In his previous talk, I remember he emphasized the crucial need for involving a statistician right from the beginning and not at the end. So without further ado, I would hand over the floor to Dr. Ahmed Mousa.
بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وكل عام وحضراتكم جميعا بخير إن شاء الله. And the primary reason for this lecture was request from some of our resident and fellows colleagues. And I always remember that one of the very pioneer ocular oncologists in Canada told me that he doesn't like at all attending statistical lectures. And I kept thinking of this, why is this happening? And I reached up to a conclusion that this is maybe because usually when an epidemiologist is giving a lecture, he jumps into equations and all these things and don't give the tricks and hints about doing the analysis. So this is why I am going to, inshallah, walk you through the process of how to deal with your data and analyze it in a nice and effective way. So we all use epidemiology and the biostatistics in gathering and managing and then analyzing data to end up with evidence on surgical intervention, on treatment modality, on how to deal with patients in a better way, and this is the main reason. So through this lecture, I'm going to go through dealing with data, starting from hints and tricks about collecting data in a perfect way, and then how to manage it nicely, store it nicely, and then end up by analyzing and producing results in a way that conveys a clear message to the clinicians in the scientific community and get good publication, which is people usually go to the results to see what's happening. So one of the questions, what makes biostatistics different from applied statistics, and what makes ocular epidemiology different? The issue is we are dealing with dynamic rather than static case. For example, if you are applying economic statistics or econometrics or so, you analyze static data. But dealing with human beings, bacteria, biological issues, you have to modify your approach to be able to capture the movement and potential movement in human beings. One of the very important issues also is what we call the unit of analysis. What is the unit of analysis? Each unit that I look at. So we have two units in ophthalmology. One major unit is the person. So we analyze data per person. When do we analyze data usually per person? When we want to look at something like his vision. So the vision may come from the right eye or the left eye as the better or the best eye, but at the end of the day, it is a person vision. However, when we do apply a treatment modality, when we do go for surgical intervention or any other procedure or therapeutic approach, we deal with eye. So we need to be careful while collecting our data to identify the intervention eye and the fellow eye, because this is going to facilitate the issue for the statistician later on. This has been a matter of investigation worldwide, and while people look at when to do this and when to do that. But the trick I want to give you is, don't do in your Excel sheet right eye, left eye. Keep them as records, like right eye of the person, then followed by another row with the left eye. What is the advantage of this? The advantage of this is that it's going to be manipulated very easily by the statistician without any confusion, as in some tests, if I want to apply some test, I have to take the left eye and put it under the right eye to make the software understand what we are doing. So this is one of the very important tricks. So before going in depth with that, let's remind ourselves by a very important issue, which is the classification of study design. A study design is the core key issue that is going to control all your research. So if you select case control, if you select cohort, if you select clinical trial, then be aware that two things will be then affected directly. One is calculating your sample size. You calculate your sample size based on the type of study design, as each study design type has its own way of calculating the sample. Two is the sampling procedure, which will be again totally different. The third issue, when you go for the analysis, some of the analysis will apply to case control, some of the analysis will apply to cohort, some of the analysis will apply to clinical trials, for example. And if you replace this, you will not be able to get your paper published, because immediately the reviewer will tell you that you used the wrong analysis approach. So watch carefully the study design. The right pyramid is showing you the level of evidence. So the level of evidence, the hierarchy of evidence, comes from down to up, from the expert opinion to case study, to case series, to cross-sectional, to case control, to cohort, and then to what we call the queen of study design, which is the clinical trial. Why they consider clinical trial as the queen of study designs? Because you minimize the bias as much as you can, which ends up by creating a very strong evidence that is not distorted by any impact of bias. Then when you review your study design very carefully, and then you decide to calculate your sample size, the next step is if you need to recruit a control. What is the main definition for control? Controls are a number of subjects that has exactly the same characteristics of the cases except for the disease. So the only one difference should be the disease. So in terms of age, gender, occupation, education, residency, whatever, it should be exactly the same. We call it in epidemiology a person who has the same characteristics of the patients except for he didn't encounter the disease. So some people may ask, how many controls do I need? So several publications discussed this issue and said that the minimum control you need is 1-to-1 to the case. So if you have 50 cases, you have 50 controls, but this is the minimum. However, you can increase the control, but make sure that you don't exceed 1-to-4. 4 controls, 4 folds of controls related to one case. And why this? Because if you, scientists found out that if you exceed 1-to-4 ratio, then the relationship may be reverted, because you are controlling the community where the disease can show up and then distort your association. So now we are ready. We know very well our study design. We recruited the cases, we recruited the controls, and let's calculate effectively the sample size. What is the actual expression of sample size? It is a piece of the population. It is a group of the population that you took them out to apply the tests, and then when you get the findings, you generalize them to the population. So it is a group of population that you have, that they have all the specific characteristics of such population. Let's say that people who live in Riyadh, for example, I take some of them, I do my investigations, I get my results and findings, and then I end up by generalizing these findings to the population. And the issue here is that it should be quite representative of the population. Cannot take it from peripheral areas, cannot take it from accumulated area, cannot point it to some people with some specific characteristics, except for some exceptional cases when I am working on a very rare disease, so I cannot take them as quite randomly. So I am allowed to take them induced sample, they call, if I'm working with a very rare disease, or I am applying a new procedure, and so on. So again, before going for the sample size calculation, there are three important considerations: the type of your study design, the availability of your data, make sure that your data are available, and make sure that you have enough budget and time before calculating the exact sample size. Then we identify the confidence interval of choice, we identify the alpha error, we will look at this, and we identify the power of our study. Sorry. So what if I'm not a statistician and there is no statistician nearby me and I want to calculate my sample size by myself? You have several options. One of these options is you go for the free websites that provide ready-made equations to calculate your sample size. So you can go for these free websites and calculate your sample size. The other option, you can use one of the many software that calculates sample size, like GPower. For example, for myself, I like the GPower, by the way. It's developed in Germany, and it's a very academic. You can use EBInfo, you can use RAB, whatever software, but you have to be sure when you enter your indicators into the cells that you are sure you are entering them into the right cell. Other than that, make sure before you enter the numbers. Other than that, you can end up by a wrong sample size that can be easily detected by the reviewer. Okay, then what if I am not sure and I cannot deal with the ready-made softwares? They need a lot of options. They, specifically something like the GPower, it needs a lot of options and so. Or I'm not sure if this website is really calculating my sample size correctly. What do? I can also calculate it manually. This is not quite difficult, by the way. But I have to watch if I am doing a community-based study or a hospital-based study, or it is a case control cohort, whatever. I should identify my confidence interval. We usually use 95% for some reasons, we'll tell you why. And let's look at some of the study designs, like for example, the cross-sectionals, which we usually use in community-based studies. So in this case, don't make the population more than 1 million. Know from the literature what is the average frequency of diseases in this area, and then identify your power and confidence interval and go ahead and calculate the sample size. What if I'm going to compare two means? If I'm going to compare two means that I have two groups and each group has a continuous variable. This is why we call mean. A very good example is intraocular pressure, because it is a continuous variable. So if I have group A and group B with different interventions and I want to compare them, this is what we called independent two groups. And if I have to apply a procedure and I want to evaluate, this is what we call dependent two groups because it is the same group. So in this case, I want to know the level of confidence interval, the power, the ratio between groups, which cases and controls, and then start to calculate my sample size. Let's remind ourselves again that about both case control and cohort study designs, they are both walking through a cohort over time. But the little difference here between the case control and the cohort is, in first, case control is a retrospective study. Always a case control is a retrospective and it cannot be prospective. When it comes to cohort study design, it can be either prospective or retrospective. But in both study designs, we have cases and controls. So we follow the cohort till the outcome happens. But when we recruit our sample, we start in case control by recruiting cases because we recruit based on the outcome. But when we start recruiting in cohort study design, we recruit them based on the exposure, not the outcome. People are exposed to so and so. And then recruit the controls. And this is showing us what is exactly the difference between people who are exposed and people who are not exposed. And later on, we will apply the statistical test when we collect our data. Let's say, for example, it is intraocular pressure because it's easier to imagine. And then see how well we analyze this. Okay, so now we didn't calculate the sample size manually yet, but we need to know what is our hypothesis. What do we hypothesize? For example, we hypothesize that applying drug A will reduce the intraocular pressure by 10 millimeters mercury. Then we identify the alpha error. We usually take it as 0.05. And the confidence interval, which is the remaining, we usually use it as 95%. These are the common values. Type 2 error, or what we call beta error, is the error that is integrating with the power. We usually take the power as 80%. So the type P error here will be 20%. And a very important thing that is the D. It is usually asked by the software or asked by the websites if you want to calculate sample size to put D. So what is D? Actually, the original issue is that you sample randomly from the community. So each one in the community has the same probability to appear in your sample. If you imagine this is what we call randomly sampling from the community. The community here can be the glaucoma patients, for example. Okay, but I am not actually taking the whole community and sample from this community, but I'm taking only target population from the whole community. This will make a difference. This difference is the D. So I put the D as 0.3, 0.5 or so, according to how I want to adjust for my sample while calculating the sample size. So my hypothesis is usually we have the null hypothesis and we have the alternative. The null hypothesis in general has a very simple meaning. Comes from its name, the null hypothesis, which I hypothesize that there are no difference between groups. I hypothesize that there is no effect size of the drug. I hypothesize that there is no association between risk factors and the outcome. And then the alternative hypothesis will be there is a difference, there is association, there is an effect size. So what is exactly the alpha? The alpha error, it is the probability that I reject each node while it's true. Immediately, type 2 error will be the opposite. It is the ability to accept each node while it is false. So these are the scientists who could distinguish the difference between randomly sampling from the whole community and sampling from a target population, and then they developed equations to adjust for this issue. What happens actually is this Professor Kish found the difference, but the high effect came actually from Bonferroni, who developed an equation to adjust for this difference. So you may hear or read in some of the publications people saying that we used Bonferroni correction, means that they neutralized the difference in the sample size to make it very easy to calculate. One very important issue, again, is the debate between the epidemiologist and the ophthalmologist. This debate comes from the fact that we may hear usually the term clinical significance. So what is quite important to the statistician or the epidemiologist is to detect the difference between groups. Okay, you agree with me? A statistician would be happy if he could identify difference between two groups. However, the clinician may not be happy because, for example, if I'm doing a study on glaucoma, for example, and say that there is a 5 millimeters mercury reduction in intraocular pressure after the surgery, post-operatively, I am, as epidemiologist, I'm very happy. I detected a significant difference. However, the clinician would say, no, this is not a difference to me. The difference would start from at least a minimum of 10 millimeters mercury between pre and post intervention. So each one is trying to convince the other, no, I detected the difference. No, you didn't detect the difference. So this will lead us to a very important point, which is we modify our equation to be able to detect the exact clinical difference, which will be of interest to the clinician, to say with evidence that I managed to solve the glaucoma problem. So this is a very important issue, and this is why we need, as Professor Khabir said, we need to discuss with the statistician a priori. So we set up together the situation, what we need to do, what are the precautions we need to take. Again, if you want to go for manual calculation, sometimes if you have something like 30 cases or so, you can easily calculate them manually. If you see the equation here, you may think that it's a very complicated issue, but it's, if you take it step by step, it's a very easy thing and it doesn't mean anything. Where the alpha here in the numerator is the alpha error, and the beta here is the beta error. The capital sigma in the numerator is the difference, and the small sigma in the denominator, which will both identify for us the target difference and the actual difference, which is the clinical significance and the statistical significance. And you can easily apply it. The letter Z is referring to what we call the tabulated figure, which is the tabulated number equal to the level of alpha and beta and so on. And we usually very simply use common figures in this. We usually take the alpha as 0.05, we take confidence interval as 95, we take beta as 0.2, we take power as 80%, and then that makes it quite easy if you even want to calculate it manually by hand. So why we usually select the 80% power? We select the 80% power because as much as you increase the power, what is the power, by the way? The power, we said it is the opposite of the beta error. The power means the ability of your results to interpret the actual difference or association. So I interpret my association by 80% correctly. I want to make it 90%. Okay, fine. I want to make it very perfect, 99%. Here, the epidemiologist will stop you, because as much as you increase the power, what will happen, because it is an equation of numerator and denominator, the sample size will shoot high. You don't want to recruit 1,000 cases for your study. It will be costly, it will be time consuming, it will be difficult to analyze and enter data and so on. So we don't ever use the 99%. No, we use them. When do we use them? When the surgeon or the clinician feels like there is a risk on life, like doing brain surgery, for example, doing heart surgery. So there is a high risk. So he wants to minimize the risk and provide very strong evidence, and then increases the power. Will not be harmful in this way. This is a hypothetical example on glaucoma calculation. We take alpha as 0.05, power as 80%, beta as 0.2, and use regular confidence intervals, and we reach up by applying the equation very simply like this, and end up by, we need to recruit 43 what? We need to recruit 43 what? What do you think? Eyes, yes. Thank you, Prof. We want to recruit here 43 eyes, because this is a glaucoma intervention. So it cannot be per person. What we usually do is, after calculating this number that we need to study, we add 10% contingency for dropouts, people who didn't come for follow-up assessments, people who didn't show up, or some missing data. So to account for this, we add 10% to the calculated sample size. So what is the exact importance of the sample size? If we remember from the first slides, because we needed to be providing high and concrete evidence and wanted to be representative of the target population. Okay, and this will show us that if the clinician insists to increase the difference from 10 millimeters to 20 millimeters, then there will be a dramatic change in the sample size accordingly. Now we calculated the sample, we are satisfied with the sample we have, we need to do the sampling. So the sampling is a totally different thing for sample size calculation. Why is it totally different? Because sampling is the process of recruiting the subjects. I know now the number, but I need to recruit them. We'll give you a very good example of that. When you conduct a clinical trial, and you know that we need 43 eyes, then we need to recruit them for 2 arms, for example, and you need to make sure that you keep the randomization. In this case, the sampling process will be one of several approaches. One of them is what we call the sealed envelope. Like the patient comes to you in the morning, you are going to the OR, but you don't exactly know what is the procedure you are going to apply. You are going to apply deep sclerectomy, trabeculectomy, whatever. You put it in an envelope and then you open this envelope in the morning. This is one thing. The other thing is sometimes it's quite difficult for the surgeons to do this. So what do? They do what is so-called the block randomization, which means that I say that the first 5 patients, I will do deep sclerectomy. The second 5 patients, I will do trabeculectomy, for example. So this is what we call block randomization, and it's much easier and saves a lot of time and effort in terms of using some consumables, using the surgical sets and logistics in the OR and all these things. So now we calculated the sample size, we recruited the sample. We need to look very quickly at different types of data as we are going to utilize them later on in the analysis. So what are the different types of data here? We know that we have qualitative data and we have quantitative data. The quantitative data is the numerical, the qualitative is what we get from observation, interviews, focus group discussions, respondent opinion, feelings like satisfactions, pain, and other things. And the quantitative actually has two main parts. Just remember that you have two major issues, the categorical and the continuous. The continuous is such as the age, the height, the weight, anything that can give me decimals. The categorical has three major types. Either it is interval, like age group, or ordinal, like what we say in oculoplastic surgery, for example, mild, moderate, severe. Nominal can be drug A, drug 2, drug 3, and so on, and can be dichotomous, like what we say, male, female. Why this is very important? Because it's going to be highly effective when we apply the analysis. Some of the statistical analysis tests doesn't apply for categorical, apply only for numerical. Some others apply again for the continuous variables, but don't apply for the categorical variables. So before selection of the most perfect statistical analysis test, I have to make sure that I know exactly what is the type of data I'm going to apply to. And just the last and the quick hint, when we go for qualitative, we go for qualitative when we don't exactly understand the issue. If we have something like new phenomena, and when we don't exactly understand this new phenomena, then I go for qualitative. I want to gather a lot of information that is I'm going to later on categorize, and I can repeat the study with quantitative analysis. So I want now to develop my data collection sheet, and I want to make it a very perfect data collection sheet. I don't want to miss anything. I don't want to be collecting something that I don't need. I want to be focused and on the point. How do I know if I'm going to do a very new study? I'm doing a very new study, and I don't know what exactly the data and variables I need to include in my study, like I'm doing my thesis, for example. And how do I develop the data collection sheet unless I know exactly what I want to do? So the major source of developing the better data collection sheet is to go for the literature. Simply, when you are reviewing the literature, filtering your findings from the literature, and ending up with 5 to 6 papers that are very close to your topic, look at the data collected by the authors. They collected age, gender, residency, whatever. They collected visual acuity, intraocular pressure, cup disc ratio. They collected refraction. See how do these 3 or 4 authors collected their data. List this data aside, and now you have a draft of the data you need to collect if you are applying a study about so and so. Will end up by this? No. You have to put 2 other considerations. One consideration is that this author may be conducting his study in Mexico, for example, or in Delhi, okay? But you have some localization that you want to put into consideration. So think of the localization of what you are collecting, because some data may not be applying to your community. Second, be sure that these variables are going to end up by achieving your goal. I mean that I can simulate an international study very nicely, but I am putting something secondary objective or so in my study that this data is not going to serve me unless I add some variables that are very specific to my study, and this is quite important. So after you list from the literature, go and localize for your topic and localize for your community and so on. And then make your data collection sheet easy to fill. Like, don't spread the variables here and there. Like what we do is put the descriptive variables together, the demographics together, the health status and history together, the clinical indices together, and so in packages. So you make it easy for your colleagues who are going to help you in filling your data, and then you make it easy for the epidemiologist and the biostatistician to look at later on. One very important tip here that you need to look at very, very carefully is when you collect follow-up assessments. If you need to apply multivariate analysis, or if you need to apply repeated visits analysis, be sure that you put all the indicators in the same set. Like in the first visit, I put the vision, the intraocular pressure, the cup disc ratio, whatever. And then the second visit, I keep them in the same order. So the statistician can very easily look at them. Some people would put IOP1, IOP2, IOP3, IOP4 together. They think that by this, they are helping the statistician. No, you are confusing him. So it's better to keep it visit by visit, and within each set, you put the same arrangement, because while the statistician is analyzing, actually, he is writing syntax to capture the variables. So his eyes or her eyes would come immediately to your variables if he gets familiar to your order of putting the variables, and can by mistake select the wrong variable. This is one thing. The other thing is don't consider them as visits, like visit 1, visit 2, visit 3. The major issue of this is that visit 3 may be at 2 months and visit 4 maybe at 7 months, for example. So when you analyze them and you want to reach up to concrete evidence, you need to make them per time, like first month, second month, third month, 1 year, 2 years. Keep them in the order per time and not per visit. This will facilitate so much your analysis process. One more thing, if you are aiming or looking at time to event analysis, like life table, Kaplan-Meier test, you want to plot Kaplan-Meier survivalship plot and so on, make sure that you are collecting the exact date of failure. People would collect the exact date of surgery, the exact date of follow-up, but they forget to collect the exact date when the surgery failed. And then if you are looking for any timetable analysis or Kaplan-Meier analysis, make sure that the statistician will ask you to go back and collect the exact time of failure, because it is one of the required variables by the software, and if you want to do something like plotting the survivalship or Kaplan-Meier test. One other thing is that what we call the combined or complicated variables. Very good example of glaucoma again is when you calculate the success rate. Success rate, severity rate in glaucoma depends on 2 to 3 variables. The value of the intraocular pressure, the number of anti-glaucoma medications, and the need for further intervention. This will help you to calculate the success rate. So the statistician is going to develop a new variable in which he will combine 3 or 4 variables to make sure that this is a success versus failure case. So if you are doing a study that needs this complication in recalculation of variables, then be sure to put them very clearly in a good order in each visit, so can be easily tackled by the statistician and make sure. One other very nice example is calculating the spherical equivalent, for example, or the refraction other than the visual acuity itself. It depends on more than one variable, so you need to put them in a very good sequence in your data collection sheet. One of the repeated mistakes is when you use something like the Kekish visual acuity scale, for example. The Kekish visual acuity scale is 1, 2, 3, 4, 5. You are quite aware of it. Be sure that when you use this, don't mix the same variable, don't mix children with adults in the same variable. And why is that? Because the adults will have easily figures that can be transformed into logmar, which will facilitate calculation of the mean difference. But when you mix them with children, which is fix and fellow and all these other things, it's quite difficult to calculate difference between two groups. It needs another procedure to calculate the difference. So this is one of the very important tricks. Sometimes the resident or the researcher would put the age as categories, 0 to 5, 6 to 10, whatever. Okay, this is fine. But my personal advice through years of experience in this, put them as numerical value and leave the statistician to categorize them in a new variable, because you will give him a wider range of utilization of what you have. So don't start by categorizing them. And if you categorize them, make sure that you are not doing overlapping. Don't say 0 to 5, 5 to 10. Then the one with 5 years, where will go, here or there? So make sure that you are not overlapping. Better to leave it as a continuous variable as is, and then tell the statistician that I have a difference between age groups, so I want to see the effect in different age groups. When you go for dates, there is another very important issue. When you go for dates, try to use the same formula. If you say like 26 of September 2024 and you put points, keep the points. If you put zeros like 09, keep the zeros. All your variables that are talking about dates. Don't put slash in one variable and put points in one variable and put hyphen in one variable and put under hyphen in one variable, because this is going to make life very complicated for the statistician. Sometimes he will need to re-enter all your date variables again, because what we do, my friends, is we calculate difference between dates. We ask the computer to subtract dates. So we need them to be very easy to the computer to understand, otherwise you will miss some of them. Again, one very quick issue about data collection sheet. When you organize and develop a very nice data collection sheet, such as this one on the right-hand side, where do you get your data from your medical record, if this is a retrospective study, for example? So make sure that when you remove values from your medical record to your data collection sheet, you remove them in the right way. For example, here we see the eyelids, we see the cornea, we see the fields. Okay, this is quite fine, but when I transfer them into a data collection sheet, I don't want to say that the upper lid was bended, for example. I want to put something that is quite clear, can be later on utilize it easily in terms of the analysis. So watch out carefully for the difference between the medical record, how it is organized, and how do you transfer your data into your well-organized data collection sheet. This is an example of what finally we get. These are the number of records. This is the age, is a continuous variable. This is the gender. This is the nationality, and so on. Some of these are numerical continuous variables. Some of them are categorical. Some of them are ordinal, which has ranks. And some of them are dichotomous. Some of them are categorical. So once we organize them like this, it is very easy for the statistician to work with. For example, I would transfer the type of surgery. If I'm going to analyze this data, I will transfer this type of surgery into 1 and 2. and make the code DS1, for example, and make the code CTT is 2. Why do we make this? We make this coding to make life easy to the software, to understand what we are comparing, what we are looking at. And I can also use mild as 1, moderate as 2, severe as 3. And this, again, will help me very well play with numbers using the software easily. But some of the errors we usually see if you write them manually and not entered by options. Because let me tell you, if the S is small, the S is capital, the M is small, you put underscore kind of thing, then the computer is dumb, it's stupid, will understand that this is a different category. It's not the same thing. And this will take time to make sure that the computer is understanding each variable by itself. So better to use them as ready-made options from the beginning to make life easy for the analysis purpose. How do we store this data later on? We store this data in 3 ways. One way, I highly recommend for you to keep the hard copy. Always keep the hard copy, by the way, because if anything wrong happen, you can go back to your hard copy and see there is an error that the station is telling you there is a wrong date, there is something wrong, then go back for the hard copy. So keep the hard copy, don't get rid of it. Second thing, you can use Excel, but Excel has its advantages and disadvantages. If you are not quite aware by the options in Excel, don't go for it. Just keep it for the data entry people to do it. Access is much, much better because Access will build an interface in front of you, and then you are entering like you are entering data exactly in the hard copy of the data form. So Access is much higher. Access is giving us another advantage is you can develop queries, you can link tables together, but you need to make sure when you link tables that you have at least 3 variables that should be in both tables. Like, for example, serial number, medical record number, whatever, but to be the same in 2 tables. Then Access will not make any mistake in linking tables for you. If you have something like household form, eye exam form, surgical form, and you want to link them all together, this will be easy given that you put at least 2 to 3 variables in each of them, which are the same variables. It's not highly recommended that you go directly for SPSS because it needs some professionalism in dealing with codes and how do you enter the records and so. But if you are familiar with SPSS, this is great and fine. But make sure that you you don't start with putting the codes, because other than that, you may forget the code, you may put it in a wrong way, you may make a mistake that you will never, and the epidemiologist will never realize as well. So it's not highly recommended to use directly SPSS. Now let's talk very quickly in the remaining time about data analysis. Before going for the analysis, we need to remember our objectives and hypothesis and the design. And what we also say that you should avoid what we call the statistical kitchen. What is the statistical kitchen? It's applying several tests before going for a real analysis plan. Usually the statistician would check here, there, and see whether there is correlation, whether there is association. So it's much better to avoid presenting your statistical kitchen. After double checking and making sure of the quality of data, one of the very best recommendations is to do a number of plots. What will these plots give me? These plots will give me, like this box plot, for example, we used for the median, will give me whether there is outliers, which are these circles above, whether there are outliers or not. I know now that I have some outliers, so I need to avoid them. It will give me whether it is normally distributed using the histogram. It will give me which category is higher, the male, female, whatever. And in this green circle in the middle, plotting correlations between two variables will show me whether there is a correlation or not, whether there is a direct correlation, whether there is a reverse correlation, whether my data are scattered haphazardly. So do some plots before doing your analysis. Two major types of analysis we usually use: the descriptive, when we describe our data, and the inferential, when we want to find associations, differences, correlations, effect size, and so on. So the descriptive, we'd go for the central tendency. We want to calculate the mean, the median, the mode, the standard deviation, look at the range, and so on, and then describe our data. Our patients were in the mean age of so-and-so, ranging from so-and-so. The majority were male. You know, all this is what we call the descriptives. When we go for the inferential, we have differences between groups, whether group A is different really from group 2 or not, association between potential risk factors and encountering a specific outcome of interest, finding correlation between variables, assessing time to event, which in Kaplan-Meier and timetables, calculate dose response in some of the clinical trials, and determining the effect size if we feel like there is an effect size of a potential risk factor on the outcome or improving the patient health. Before selection of the most appropriate statistical test, we go for our hypothesis again: type of data, sample size considerations, study design, and type of inferential analysis we want to apply. The type of hypothesis will lead us in selection of the most important statistical test to apply. Type of data will help me. I apply statistical test that is applied for categorical variables or continuous variables also. Sample size will direct me whether I go for parametric analysis or non-parametric analysis. Study design again will guide me if I go for odds ratio, relative risk, chi-square, or whatever. So very simply, take this rule very easily. If your sample is relatively small, go for the non-parametric because the parametric will not be indicated. If your sample is high enough, test the normality and go for the parametric analysis. And we will see how it differs. Looking at the study design, if I have a case report, this I'm describing diagnosis of a case, intervention for this case, and outcome of this case. So all I need is descriptive analysis. If I have a case series, which is a group of patients having the same diagnosis, I went with them through the same treatment modality, I ended up by the same outcome. Again, I can use some potential inferential analysis, but the major will be descriptive. In cross-sectional studies, I can use chi-square, which creates association between variables, odds ratio, which will give me the likelihood of encountering disease, for example, by females rather than males, and so on. In cohort studies, go for the relative risk, and this is, by the way, very important. If you are writing a very good paper and you applied odds ratio for a cohort study, the reviewer will tell you, no, odds ratio doesn't apply actually for cohort. You see, this is the impact of selection of the most appropriate statistical test. So when I go for testing the significance, I identify the null hypothesis, state the alternative hypothesis, set the level of significance, select the most appropriate statistical test, and then compute the test, which will end up by a p-value. Then I say that, yes, there is a significant difference or not. Okay, so there is a very quick hint on that. is that when you go for descriptive analysis, try to well describe your data in terms of all the indicators before going for the potential associations. Now I'm going to analyze my data very quickly. If I am collecting one group, let's say I have only one group, and this group has continuous variables, so I can go for the t-test. If they are nominal in nature, I can go for the chi-square and find associations. If it is ordinal, then ordinal means ranked, then I can go for the Kolmogorov-Smirnov test. Let's say that I have two groups, for example. If I have two groups, I should look first whether they are dependent or independent. The independent means that I applied intervention to group A and group B to separate. The dependent here means that it is the same group, but I applied pre-intervention assessment and post-intervention assessment to the same group. So this is the difference between dependent and independent groups. And why this difference is important? Because we have several types of chi-square. People may know not that. We have 6 types of t-tests, for example. So to select t-test for independent or to select t-test for dependent will rely much on whether the data actually comes from dependent groups, which means again pre and post intervention, or post intervention last follow-up, for example, or I'm doing comparing two groups. I applied intervention A, applied intervention B, or I am comparing cases to controls. That's what we call independent groups. Then if I have 3 or more groups, I go for the ANOVA test, which is analysis of variance. It's quite similar to the t-test, but it is applicable for more than 2 groups. And of course, if I go for if I go for non-parametric, I would replace the ANOVA test with the Crucial-Wallis test to suit with the smaller sample size. The correlation, again, will find whether there is an association between 2 variables or not, means that if this variable A increase, variable B will increase. If variable A will decrease, variable B will decrease. This is what we call directional. But if it is a reverse relationship, means that when variable A increase, variable B will decrease. And this is what we call reverse relationship. And of course, we go for Pearson correlation test. In case of we have parametric, means sample size is enough, saturated, and we go for non-parametric, we use Spearman instead of the Pearson. So if we go back, we see that each statistical test in the parametric has its alternative test in the non-parametric that will adjust for fewer sample size or abnormality in distribution. So what is the effect size? If I have repeated variables or model, I'm doing regression analysis, for example, and I have several variables that are affecting one variable, like age, occupation, and so are affecting cataract, yes or no, then we need to assess 2 things here. The value of beta, which is the exact effect size, and the p-value, which will give me the exact significance level. Now, just will give you some very quick, simple hints from practice. When you use mean, when you calculate mean, calculate the standard deviation and the range. If you calculate the median, you have to calculate the interquartile range, and you cannot use the regular range, for example. Sometimes when we measure something like in basic science tests, for example, we don't use the standard deviation because we are using measures. So we use a standard error instead of the standard deviation. When we report our data, some people would say the chi-square was 3.6, the p-value was 0.03, for example. we don't need the exact value of the chi-square or the exact value of the t-test, because they can be easily understood by statisticians, but not by the ophthalmologists in the scientific community. But if we go for correlation analysis or regression analysis, then we need to report both the R value, which gives me the strength of association, and the D value, which will give me the exact effect size in regression. So when you use, very simply again, if you go for chi-square, you go for t-test, don't mention the value of t, the value of chi. Mention only the p-value. But if you go for regression analysis, if you go for repeated measures analysis, if you go for example, correlation analysis, report the R, because the R, which is the correlation coefficient, will give you the strength of correlation. The D of the regression will give you how much is the effect size of these variables. Now, the last section, wanted just to give you some hints. When you finish all this and start writing your results, you need to package, and remember the word package, you need to package your results section in a way that satisfies the reviewer, one thing, to make your paper through. Second, to convey a very clear message to your colleague, the clinician who is reading your paper. So, one thing we need to remember about the results section itself, that it is a tough section. What does it mean it is tough section? Don't elaborate on the results, don't justify, don't explain anything, don't interpret. Means that when you say that intraocular pressure has been decreased by 10 millimeters because the drug was good, this is wrong. It is very tough section. You just say the findings. The explanation will come later on in your discussion. You can justify, you can interpret, you can put your opinion, but never do this in the results section. Start with your descriptive part always. Say that we recruited 20 cases, they were in the mean age of so, the gender was mainly female, 10% of them had asthma, whatever, and then go step by step. This enables the reader to get what you are doing later on. Then start by, we detected association between so and so in the inferential section. We found that there is an effect size. We found a difference between groups, and so on. If you write your results, by the way, the most difficult part of the manuscript is the discussion. This is why they say that the most senior co-author is the one responsible for writing the discussion. So I promise you, if you write a very good and well-packaged result section, take it step by step, and you can write accordingly a very important discussion section. So in the descriptive part, as we said, we describe our cases, and then when in the inferential part, we say the association, differences, and so on and so. What we need to avoid is the statistical kitchen, as they said, too many details. If they are not necessary, don't mention them. If you have negative results, you have to clarify them and clearly demonstrate them, because they are quite important as the positive findings, by the way. And avoid also interpreting anything that you found in your results section. Now I very well packaged the results section. I want to plot some graphs. First thing that's very important, try to select the indicated graph. Like a pie graph is representing pieces of the whole cake. Some were male, some were female, some were severe, some were mild. Correlation, use scattered association diagram. Use the box plots when you are talking about means, because it's very specific for means. And use this time graph when you have to show, for example, that visual acuity changed from 6 months to 6 months to so and so between the two groups. Then selection of the most appropriate graph presentation is quite important. This is one thing. The other thing that you need to carefully know that don't repeat the table in a graph, because this is called redundancy and will be immediately rejected by the reviewer, who is a specialized person. You can start with saying that the age group was so-and-so, the mean age was so-and-so, the rest of demographic figures are explained in table 1, and leave it like this. But never plot something that you exactly mentioned in your text in details. Never put something that from exactly the same table, because this is going to be a defect in your study. So when we use graphs, usually we use graphs when we want to make the reviewer or the reader or the audience get a one-shot understanding of what's happening. This intraocular pressure has decreased much in the intervention group rather than group with placebo. So we want to shoot in one thing that what happened. So this is majorly when we use graph. When we use a figure, when we use a table, we have a group of variables that are highly related to each other. We want to show them and show differences and show the p-values between groups. When we use text in two occasions. One of them is if I have a subset, like I have 50 cases, 10 of them had a specific complication, so I don't want to put them in the table. I want to say that within our series, 10 cases faced complications, so and so, so I want to put them in 2 to 3 lines. Or I have a specific group, like I had, as I mentioned at the beginning, that don't mix readings of visual acuity of children with adults. So I can analyze data and then end up by saying that we have a subset of our series which were underage to get visual acuity. Their vision has improved according to the treatment modality or surgical intervention and so on. So this is why I go for the text. The other thing, never put your data in the table and that's it. Don't expect the reader to understand exactly what you want to say. So when you put a table, you have to write 2 to 3 lines to explain your table later on, after putting the table. Okay, thank you very much. I hope that it was not very boring to you, and I hope that I could put some effective hints to you. I'd like to again congratulate you for coming back, and thanks to the research department and Kekesh for inviting me to the lecture.
This was an excellent talk, Dr. Ahmed Mousa, and thank you for coming and spending the Eid here because of the scarcity of flights. So the floor is now open for questions, and if you have any questions.
Thank you, Dr. Mousa, for coming to give us this very informative lecture. Do you have any experience with the ChatGPT regarding how to design the data before we do our research?
Well, it's the ChatGPT and AI Author, which is more specific for scientific work, and all of the open artificial intelligence have till now a lot of help if you want to do literature review, if you want to organize your writing, if you want to gather information about the topic. But in terms of conduct the analysis, there are some trials. These trials, and even before the artificial intelligence, by the way, some of the pioneer biostatisticians developed syntax on Excel and on SPSS and on Stata. Professor Khabir knows this, that you can apply for your data directly, like ready-made syntax you can apply even before the artificial intelligence. So this is macros and syntax are already available. The problem is when using artificial intelligence is two things. One thing is that you need to give the exact idea to the artificial intelligence on what you want to do, and avoid, distracting here and there. And the other issue is sometimes it collects that I have tried this, by the way. It collects data that you don't need, because what it does. By the way, my friends and colleagues, artificial intelligence is going into a very more stronger phase now, which is, they call it artificial super intelligence, which is building on the experience from artificial intelligence to make it avoiding mistakes, pitfalls, doing more sophisticated work. That's what they are calling now artificial super intelligence. And I think that using it in research is now quite common, specifically not at ChatGPT. Maybe the AI author is much more stronger, actually.
So there was one comment I want to make, and just from what I gathered from your talk and from the slides is that, ophthalmology is a very complex specialty, unlike public health, which is about the obvious, and prevention is about the obvious. I give you the example of COVID, and I've always been citing this. Like the COVID was about 4 or 5 variables: social distancing and hand hygiene, and towards at a later stage, then we had vaccination. And so these only 3 variables, people were able to prevent millions of deaths. Problem with ophthalmology is that you have too many specialties, right? And subspecialties, and then you have too many variables. Like in interior segments, you have more variables than you have in maybe the entire public health. So it's very important that any data that is collected has to be taken seriously by the investigator, the way it is collected. The follow-ups, for example, in glaucoma, there are too many follow-ups. One data I was analyzing had 27 follow-ups. Now one has to make sense out of that data. So, and then there are lots of follow-ups, and people don't come at 1 week and 1 month and 6 months and 1 year. They have their own way of coming to hospital depending upon the seasonality. So all, and the 2 eyes. It's not just 1 eye. If you exclude 1 eye, that means you are losing important information. And so it's very important. So and it involves complex analysis, like if it involves follow-ups, multiple follow-ups, 2 eyes, missing data. This is the next level of epidemiology and statistics. So, and a lot of patience is needed. Also, you talked about the dates. Dates are very important if you're having follow-ups. If there is an error anywhere in these dates, it will not be accurately reflected. One issue we find, for example, like the date of presentation, that's my habit. So the date of presentation and date of birth, I just subtract, and some people presented before they were born. So, these are, it needs a lot of patience also. Like so anyone who is involved in a longitudinal study that involves follow-ups, the investigator has to take, has to lead from the front and make sure that all the data is accurate. And the coordinators, there is a lot of coordination that is needed. So it has to be very well coordinated also. There is a question at the back. No?
Thank you very much, Dr. Ahmed. So since you mentioned the problem with the irregular follow-up dates, what is the best way to get around this problem? Like, we don't have patients coming in 1 month, 3 months, 6 months, 1 year. So let's say we collect data for 2 years. Is it better to just group them as early follow-up last follow-up, or what's the best solution?
And sometimes according to the common way of publishing data, like for example, in cornea studies, in refraction studies, in glaucoma studies, we need to say that after exactly 3 months, after exactly 6 months, as there is a threshold of stability of the eye. So the best way is just to mention the visit date in the same format as the previous visit date. And if we keep this, we can easily subtract dates from one another, given that they are in the same format. And then it will give us whether this was 3 months or 6 months or 4 months or drop out or whatever.
Yeah, so I think it's a very good question. The Glaucoma, World Glaucoma Association, they have published a guidance on how to take care of this. For example, somebody did not present at 6 months, but presented at 8 months. So, that whole period is considered as 6 months. Sometimes the problem arises like somebody presents 3 or 4 times during that period. So that has to be taken care of as well. And one comment about matching, like you also mentioned about matching, and like how many variables, like people often tend to match on too many variables, and so it's always nice to or good to match on 2 or 3 variables at the most. If you're matching on too many variables, it will become a problem. You will remain single for the rest of your life. Any other? Do you have any other question, comment?
I have a final comment. As Professor Khabir mentioned about the COVID-19, this will lead us that although there are what we call outbreak investigations, and so it's not only in ophthalmologic research about conveying a message to clinician. It's also about giving guidelines for prevention of a specific disease from reaching up to blinding disease.
So thank you very much, and we are so honored that you came all the way from Egypt, and thank you so much, and thank you for Dr. Kadir for the time you give us. Thank you, and thank you everyone, and for patient listening. Thank you.